Assalamualaikum warahmatullahi wabarakatuh. My name is Amirul Ashraf Al-Madani. Now I will be explaining on how I did the part A, complex system consists of multiple subsystems. So the task is to execute the assembly design and obtain the response of the system, which is YS at the output. So we need to construct back the figure 2. So this is figure 2, so we need to construct this figure 2 back into the Simulink. So now we'll be opening MATLAB, then we can choose new and then we click the Simulink model, or we just can go through right here. So we click this, and then if you have done the Simulink, so you can click on this, but I had done it. So this is basically the Simulink, the block diagram in Simulink, which I constructed back from the sheet. So this is the unit step function. So this is the subtract, gain, integrator, sum, and so on. So this is the clock. So the clock we save it to workspace out.t, and then the output we save to workspace also out.y. So if you run this, so we double click the scope. So this is basically the graph for this Simulink diagram. If we open the MATLAB, we can see the variable. So this is the variable of out t, and this is the variable of out y that we run just now. So I think that's all from me. Thank you.
Hi Doctor, today I will be demonstrating on how to use reduction of block diagram using reduction method. For this case, we will be using cascade form, parallel form, and feedback form, and moving block to create equivalent form. First and foremost, I will transfer the values into the G and H form. After that, I will bring out G1 out of this, and then I will create a G2 over G1. I will be using moving block to create equivalent form. Then I will be using feedback form for here, and I will be using parallel form over here and feedback form over here. And then I will create an equation like this, and then I will use the cascade form, which will be multiplied to each other, and then I will form an equation like this. After that, after I create the equation like this, and I will start to transfer the value of G1, G2, G3, H1 and H2 and H3. After transforming the values over here, and I will simplify the value into this, and then I will times in s power of 3 to remove the denominator, and I will obtain this answer. That's all from me, and Shashi will demonstrate the method rule.
Hello Dr. Sadikin, I'm Shashi from Group 6. Now I would like to explain about Part B, reduction of multiple subsystems using the Mason's rule. So first of all, we have to find the equivalent single transfer function by using Mason's rule. Mason's rule is actually a technique by using one formula that was derived by S.J. Mason for reducing signal flow graphs to a single transfer function. There are actually two main components in Mason's rule, which are loop gain and non-touching gain. So here is the block diagram that has been given in the lab sheet without the reduction method. first and foremost, we have to create the signal flow graph. This signal flow representation consists of two elements. First one will be our nodes, which represent signals, and secondly, lines with arrows, which represent the subsystems. Summing junctions and pickoff points are implicit in signal flow graphs. These graphs are helpful in visualizing the meaning of the state variables. After creating the signal flow graphs, we need to identify the forward path gains. In this case, there will be two forward path gains. Then we have to identify the loop gains too, which are G1H1, G4H2, and also G6H3. Then we have to identify the non-touching loops 2 at a time and also the non-touching loops 3 at a time. So here the non-touching loops have been combined. At first, the 2 at a time is G1, G4, H1, H2, G1, G6, H1, H3, G4, G6, H2, and H3. And 3 at a time will be G1, G4, G6, H1, H2, H3 after combining all. After creating the signal flow graphs and identifying the loop gains, non-touching loops, everything, we have to substitute all the values into this Mason's rules equation. So here, as we can see, T1 equals to G2, G4, G5, G6, and T2 will be G1, G3, G4, G5, and G6. So next will be the delta. The delta is actually 1 minus summation of the loop gains plus all the summation of non-touching loops 2 at a time and minus the non-touching loops 3 at a time. So the delta 1 will be 1 minus 0 equals to 1, and delta 2 will be 1 minus 0 equals to 1. After that, to obtain the transfer function, we have to T1 delta 1 plus T2 delta 2 over the delta. So once we substitute all the values of G2, G4, G5, G6, H1 and everything, we will get the transfer function, the equivalent transfer function of the system, which is 30s plus 30 over s cubed plus 10s squared plus 31s plus 30, which is completely similar to the reduction block diagram method. Once all the calculations done, now let's look at the MATLAB Simulink model. So as we know, the transfer function we obtained is 30s plus 30 over s cubed plus 10s squared plus 31s plus 30. So we can insert this numerator and denominator value in the transfer function block to obtain the transfer function's response. Once all set, we can press the run button. After we press the run button, we will obtain the response of the transfer function, which is similar to part A. That's all from us. Thank you.